Thank you for the introduction. My name is Congyu Liao. Today, my topic is high-fidelity mesoscale diffusion MRI on NexGen 70 using gSlider. So firstly, I want to briefly highlight why the NexGen 70 is valuable for mesoscale DWI. The NexGen platform provides a much stronger gradient system, which enables higher Gmax for diffusion encoding, shorter echo spacing for EPI readout, and a shorter echo time. And for our gSlider project, this reduces TE from 61 millisecond to 41 millisecond, corresponding to about 33% SNR increase at 0.6 millimeter resolution. In addition, the 96-channel receiver head coil could further improve SNR for high-resolution diffusion MRI. Next, I will briefly introduce gSlider-SMS technique. The main idea of gSlider is to improve SNR efficiency with volumetric slab encoding rather than conventional simultaneous multi-slice imaging. Here, we use 5-fold gSlider encoding with multiband 2 acquisition, where each slab is encoded by 5 different pulses with different slab profile. And these thin slab are then combined during the reconstruction using the RF encoding matrix to resolve high slice resolution images. These slides highlight the benefit of using gSlider at 70. The main point is that compared with the conventional SMS EPI, gSlider is much more SNR efficient when using shorter TR. The image on the right clearly show this as we see about 2-fold SNR boost. Another nice feature is that gSlider is self-navigated. It's robust to short phase variation and head motions. This feature makes gSlider a very attractive approach for high-resolution diffusion imaging. However, there are challenges of gSlider at 70. First, gSlider uses RF encoding, which is sensitive to B1 plus in homogeneity at 70, which could cause image intensity and non-uniformity. Second, the T1 value at 70 is longer than 3T, which could cause incomplete T1 recovery at a short TR, leading to slide boundary artifacts. So we propose several approaches to address these issues at 70. First, we add MR fingerprinting pre-scan to obtain T1, T2, and B1 plus information for robust correction. Second, we propose a voxel-wise implant correction to improve the robustness to B1 plus in homogeneity. And third, we propose a through-plane correction to reduce the slab boundary artifacts. With these approaches, we are able to achieve 0.6 millimeter isotropic resolution diffusion with high image fidelity. Here is our acquisition and the reconstruction pipeline for 0.6 millimeter ISO gSlider DWI. We start with 5 minutes MR pre-scan, which provides 0.6 millimeter quantitative T1, T2, and B1 information. Then we acquire gSlider data with 2 shell B equal to 1000 and 2500 with 64 diffusion direction for each shell. After the gSlider acquisition, first, we co-register the quantitative map with the diffusion data. Then we do the simulation of signal dictionary using block equation. Based on that, we perform in-plane B1 correction and the through-plane slab profile correction, followed by AI denoising. With this pipeline, we can generate 0.6 millimeter isotropic DTI with improved image fidelity. Let's discuss this step in more detail. So after aligning the quantitative T1, T2, and B1 plus map to the diffusion data, we perform a block simulation of gSlider sequence across different T1, T2, and B1 values to build a signal dictionary. After building the dictionary, we can generate a normalized signal scaling map, voxel by voxel from the dictionary to correct the in-plane B1 in homogeneity. As shown in this figure, without the correction, there are intensity variation across the brain. And by applying the in-plane correction with the scaling map, we can compensate for the signal variation and achieve more uniform diffusion imaging across slice and B values, I can switch back and forth so you can see the improvement after the implant B1 correction. And after the implant correction, the next step is to address the through plane slab boundary artifacts. Here we incorporate the through plane B1 plus in homogeneity and T1 spin history effects into the gSlider forward model to mitigate the slab boundary artifacts. The plot show the slab profile varies under different T1 and B1 values. And with the through plane correction, the reconstructed image at the bottom show the slab boundary artifacts is much mitigated. So after this correction, the final step is AI denoising. So here we apply a CNN transformer-based denoising network with G-factor and a scaling map to further reduce the noise while preserving fine image structures. As what we can see, without the image denoising, both colored FA map and ODF at 0.6 millimeter isotropic resolution is very noisy. And with AI denoising, we can see both color FA and ODF becomes much more cleaner. Here is our diffusion imaging protocol on NexGen 7T. We can generate two shell 128 diffusion direction, whole brain 0.6 millimeter ISO DWI in 40 minutes. And with impulse gradient, we can achieve TE of 41 milliseconds, which is much reduced from the previous like a standard 7T. And we can only need like a 15 seconds to acquire one diffusion directions. Here I show preliminary results focusing on tangential fiber orientation in S1. As shown in the zoom in region, the fiber orientation in M1 is radial, and in the adjacent S1 region, it becomes tangential. This pattern is consistent with previous reports in literature. Here I show another preliminary results in V1 region. In both ODF and tractography, visualization can see a clear tangential fiber pattern in the cortex. This is consistent with the lines of Gennari in V1, which is known to have a strong tangential organization. So this gives us an example that our high-resolution diffusion approach can capture the fine intracortical fiber structures in vivo. Lastly, we are extending our gSlider data to automated fiber quantification AFQ. By combining the gSlider diffusion data with the MRI of T1 and T2 maps, we can perform tractography and automated bundle segmentation and long track profiles of FA, MD, T1, T2. This provides us a unified framework for studying white matter microstructure with both diffusion and reflexometry data. So in conclusion, in this project, we achieve whole brain mesoscale diffusion MRI on the NexGen 7T using the gSlider acquisition, and we propose the in-plane and the through-plane correction framework for high-fidelity gSlider reconstruction. And we also, our preliminary in vivo results show the tangential fibers and combined reflexometry diffusion studies. And in the future work, we plan to develop a PTX version of gSlider to further improve image uniformity, and we will further push toward even higher spatial resolution. So finally, I want to thank the U24 NexGen 7T MRI pilot project. Thank you very much.